So the question that's begging to be asked is, how do I solve these guys? Side, side, side triangles and side, angle, side triangles. So clever. It's just so clever. So, I mean, let's say that, for example, I have a triangle that looks like this, right? Well, that's terribly drawn. I don't know. Let's call this A, B, C. How am I going to solve for anything? Because I don't have any angles. The answer to that is the law of cosines. I'm going to prove it for you real quick because it's pretty clever and it's fun to watch. Okay? So watch this. I'm going to take this triangle and cleverly put this angle, so angle C, I'm going to put it on the origin. And then I'm going to try and replicate it as closely as I possibly can. All right, so this distance right here, this is side B, this is side A, and this is side C. Okay? Now, I'm going to call this angle C, but just for simplicity's sake right now, I'm going to make it theta. Okay? I'm going to do a really clever little trick here. I think you'll like this. Notice, remember from geometry, you can twist, flip, orient triangles. I can move them around, and as long as I've got an isomorphism, it just means it's the same form. So it doesn't matter that I've moved this thing over to the coordinate plane. Let's name this point right here. This point is B comma 0. True? Now, I'm going to name this point for a second. And that may take a little bit of thought, but let me change the color of my pen here so that we can see. Do you all agree that this right triangle right here, if I were to call this X and this Y, then I could name this point X comma Y, right? Now think about this for a sec. I've got theta and I've got A, right? So don't I know SOHCAHTOA tells me that sine of theta equals y over a, which implies that y equals a sine of theta. Similarly, the cosine of theta equals x over a, right? So ka adjacent over hypotenuse. So x equals a cos theta, right? I'm going to change color of my pen so I can put this back down. So doesn't that mean that the name of this point is a cos theta comma a sine theta? True? Now, watch. How can I figure out C? Well, just for fun, can't I use the distance formula? Right? Can't I use the distance formula? Well, or I could actually use, another way, I could just use Pythagorean's theorem. Pythagorean's theorem says that C squared, so now I'm dealing with this right triangle, or I can use distance, it doesn't really matter. Remember, distance is the same thing as Pythagorean's theorem. But let's set it up. I know that C squared, the distance of C squared, is equal to, A cos theta minus B, that's a cos, by the way, not a 5, squared, plus a sine theta minus 0 squared. So in a puff of algebra, I know that this is equal to a squared cos squared theta minus 2ab cos theta, right? Because it's this times this twice, which gives me that, right? Plus a squared sine squared theta. Whoa. I missed a b squared in here, didn't I? I'm sorry. Plus b squared, sorry about that, plus a squared sine squared theta. Well, let's see. What does that mean? This means I can rewrite this as a squared times cos squared theta. I'm just grouping my terms, plus sine squared theta. See, I'm just grabbing this term and this term, plus b squared minus 2ab cosine theta, right? Well, this is getting even prettier. What's cos squared plus sine squared? It's 1. So this turns into a squared plus b squared minus 2ab cosine of theta, which really, in the context of if this is angle C, this is angle A, and this is angle B, then this is just a squared plus b squared minus 2ab cosine of C. Now, similarly, don't we know that a squared is going to, because if I just reorient the triangle, won't I get that a squared equals b squared plus c squared minus 2bc cos A? Similarly, b squared is going to equal a squared plus c squared minus 2ac cosine of b. Man, those mathematicians were freaking good. Now, the cool thing about law of cosines, is when we solve for angles. So let's do one. But let's think about this. When we solve for angles, when I solve for angle B, aren't I going to have to use the inverse cos? Well, what is the range of the inverse cos? It's from 0 to pi, isn't it? So it will give me obtuse angles, which is wonderful because the law of sines does not. All right, let's do that here.